So today is our, let's say, penultimate lecture. Penultimate topic is, I'm going to talk about Kontsevich deformation quantization, Kontsevich construction, and some formulas as well. It usually takes about one lecture to give some details. So if it goes as planned, the next time I'll just give some example. An example of how Kontsevich quantization helps us to prove things. And also next time, so today we don't have any seminar today. We're not meeting in the afternoon. We just talk just this lecture. But next time we'll have a seminar, so probably the next time we'll have a test, our final test for which you need to pass to get your credits for this course. Okay. So let me return to the idea of Kontsevich quantization. We have two differential graded algebras. One, the algebra of polyvector fields on some manifold M. We extend it by adding formal variable h bar. And also, it is convenient to shift the dimensions. As you remember, if you take two polyvectors p and q of degrees small p and small q, and there's Houghton bracket, it will be in degree p plus q minus 1. And that's not what we would expect, what we should expect when we speak about differential graded algebras. So in order to reconcile the situation, we need to shift it by 1. I really don't know whether 1 should be written here or maybe somewhere here. I don't know which is better. It means that the p polyvector field will have degree p minus 1. And the q polyvector field will have the degree q minus 1, of course, so that their commutator will have the degree p plus q minus 2, which is precisely the sum of the degrees of p and q. Once this is done, and some precautions concerning the signs are also taken, this is the genuine differential graded Lie algebra when we take the differential to be equal to 0 and the bracket to be equal to this Houghton bracket. The same thing should be done in the case of polydifferential operators on the same manifold, also extended with formal variable h bar. It also should be shifted for the same precise reason. After shifting and some work with signs, it also becomes the genuine differential graded Lie algebra with respect to the differential delta, the Hochschild cohomology differential. And the bracket given by the Gersten-Haber bracket. one knows that these two algebras are in fact closely related by the Hochschild-Kosten-Rosenberg theorem. Namely, there exists a map chi, sometimes mapped with these three symbols, Hochschild-Kosten-Rosenberg, from left to right, which induces the isomorphism, induces an isomorphism probably, an isomorphism in cohomology. When I say that something induces an isomorphism in cohomology, I mean that it induces the isomorphism on the level of the Lie algebras. Because, of course, the structure of graded Lie algebra is inherited on the level of cohomologies on both sides. So we can say that, in fact, Hochschild-Kosten-Rosenberg map, even though it is not a homomorphism of Lie algebras, it still induces an isomorphism cohomology on the level of Lie algebras, of cohomology Lie algebras. We also know that the Poisson structure Poisson bivector and the associative star product verify certain equation in these differential graded Lie algebras. This equation is called the Mauer-Cartan equation. And it goes as follows. An element omega of degree 1 in a differential graded Lie algebra G is said to verify the Mauer-Cartan equation if d omega plus 1/2 of omega comma omega is equal to 0. On the left, the differential is trivial, so this equation amounts just to the condition that a bivector, because an element of degree 1, after shifting as you see, corresponds to a bivector. That a bivector verifies this identity. And here, an element of degree 1 is again a formal power sum of cochains of degree 2. And the condition is that delta B plus 1/2 B comma B is equal to 0. It is precisely the associativity condition. Here you can add 1/2 and a differential, trivial differential. So both verify the same equation. Thus we are naturally brought to the following question. Suppose you have two differential graded Lie algebras, say G and H. So the standard abbreviation of differential graded Lie algebras is DGLA. If you run across this abbreviation in a text, you should know that it stands for these 4 words: differential graded Lie algebras. Okay. Suppose we know that the cohomology of G is isomorphic to the cohomology of H. Suppose. What can we say about the sets of Mauer-Cartan elements on the left and on the right? On the left and on the right. So MC stands for the Mauer-Cartan elements. Of course, if there exists a homomorphism, an existing homomorphism, chi, say from left to right, well, we can assume that it induces the isomorphism cohomology. Such homomorphisms are called quasi-isomorphisms. When you have a homomorphism of differential graded Lie algebras which induces the isomorphism in cohomology, then it's called quasi-isomorphism. Then, if we take the image of any Mauer-Cartan element on the left, we'll have an element of the set MC of H on the right? Because, of course, the homomorphism preserves, any homomorphism preserves the Mauer-Cartan equation. But unfortunately, in our case, chi, even though it induces an isomorphism cohomology, does not induce isomorphism on the level, it's not a homomorphism of Lie algebras, right? It doesn't send a commutator into commutator. So we need to modify our construction. And last time I suggested the following idea. Definition. A map, one says that there is an L infinity morphism between 2 differential graded Lie algebras, let me denote it by F, from G into H. I use this kind of arrow to distinguish these kind of maps from the usual maps. It's not a usual map. It's in fact a collection of maps. Namely, so F is the sequence, maybe infinite sequence of maps Fn for all n greater or equal to 1, such that Fn is in fact a map from the exterior power of G, the nth exterior power of G, into H. You should be very careful here, because what does it mean to take an exterior power of G? It means, in fact, that if you take, so you take tensor product of n copies of G. And then I quotient out relations which look like the relation we use to define the usual wedge product. V tensor W is equal to minus W tensor V. But in this case, you really need to take into consideration the degrees on the left and on the right. So it's something like minus 1 to the power degree V minus 1 degree W minus 1, if I'm not mistaken. You see that the signs are quite important here. Let me check if I'm not mistaken, if I haven't made a mistake about the signs. So if V and W are even, right? Yeah. So it will be minus, right? So if this is minus, so this will be plus, in fact. And that's okay in our case, because I quite forgot to say that, okay, let me put lambda here, then put tilde here, because in fact, I really don't want to get deep into details, but I think you need to make another shift here before you do this. So let me put this here and just use this sign rule. This sign rule is correct. But maybe you need to, if you want to identify this kind of product with the usual wedge product, you really need to make another shift before you do it. Okay? I just don't want to get further into details. I think, well, if you really want, let me do it like this. Okay, then it will be usual shift. usual wedge product. Okay.
So without this shift we get this grading, but if we shift it we will get usual wedge.
Okay, I mean, see, if you consider, you see the problem is that this minus 1 and this minus 1 show up because I use this gradient first, use this shift first. Without it, we'll just have this minus this, just this. Okay, a degree, so in this case, a degree of f n should be equal to 0 in this sense when you take the shifting. But if you take the non-shifted version, then it is 1 minus n. It should be 1 minus n. Okay. When I say the degree of a map, it means that I take the sum of degrees on the left, take the degree of the image on the right, and take the difference. So the difference of the image, of the degree of the image and the degree of the origin is called the degree of the map. So in our case, I think it's a good exercise to see that these two degrees actually match. This n shows up because I neglect the shifting on the left and on the right. This 1 shows up from the shifting on the right, and this n shows up from the shifting on the left. Okay. But that's not all. It's just part of the data. Most important part here is the following. For all n, the following equation should hold. Delta f n plus 1 applied to x0 xn is equal to sum for all I less than j from 0 to n, fn xi xj, the commutator of xi and xj, then we put all the remaining terms except for xi and xj. As you see, there are as many as n terms in this sequence now. This one plus n minus 1 remaining terms in the sequence. Of course, there should be signs in front. These signs depend on the degrees of x1, x2, and so on, xn, and on the positions of xi and xj. So it's quite difficult to write down all the signs correctly. But roughly speaking, every time we change the order of xi and xk for some k, we need to introduce this kind of sign. That's what they call the Kasul sign rule. But that's not all. We need to add, again with sign, the commutator of fp x s1 x s p and fq x s0 p minus 1, right? P, sorry. X. It's a bit difficult. Probably better to use this. Then I have this ordering will be easier. So first of all, we need the sum here is taken over all p and q such that they sum up to n plus 1. S is any element in the group of permutations of n plus 1 elements. And if we just take all permutations of the prescribed form, then we need to renormalize these by dividing out the number of elements we just permute first p and last q terms in this permutation. Or else we can just take into consideration only the permutations which preserve the order of the first p terms and the last q terms, but change the order between these two groups. Such permutations are called shuffles. So sometimes you will find a formula where instead of Sn plus 1, you will have shufflings and no terms like no factors like these show up. The main purpose of this definition is the following theorem, or probably proposition, which I am going to prove now. Proposition. Suppose we have an L-infinity morphism F from G into H. Then, for every Mauer-Cartan element, omega, in G, the following formula, f of omega equal to the sum for p going from 1 to infinity, 1 over p factorial, fp of omega, comma, omega, p times, determines an element in the Mauer-Cartan set of H. Of course, under the evident condition that this formula makes sense. That is to say, that this sum, that this series, formal series, actually converges in one or another sense. For instance, this happens if there is only a finite number of non-zero terms here, but also it can happen if there is some kind of topology on the right such that this series converges in this topology. Okay? Let's prove this. To this end, we apply the differential to f omega. It will be equal to sum over p 1 over p factorial delta f p omega omega. You see, there is a difference between this delta of fp and this delta of f applied to something, right? There is a difference. In order to obtain this finite result, we need to add and subtract the terms which actually make this into delta of f applied to something. Namely, we need to subtract and then add back elements of the form fp of delta omega omega plus minus fp of omega delta omega omega and so on. Right? So let's do this. First of all, we observe that the signs which appear will all be equal to 1, and that's because omega, after shifting, it used to be degree 1, but after shifting it becomes of degree 0. So it commutes with everything. There are no signs we would need. So it will be equal to sum 1 over p factorial delta fp applied to omega comma omega, right? And here we need to add back these missing terms fp, but there are exactly p terms like this. And since, as I told you, omega is of degree 0 after shifting, they all are the same. So there are p terms, and we get fp of delta omega comma omega, and divided by 1 over p minus 1 factorial. Okay? Nice. Let me continue here. First, I'm using this formula, this equation. Delta fp applied to omega comma omega is equal to fp minus 1 applied to omega comma omega. And there will be exactly as many terms here, as many different pairs of omegas I can choose from the string of p omegas, right? How many are there? Well, this is binomial, second binomial coefficient of p, right? Yeah, precisely. So it's p minus 1 divided by 2. And there are no signs for the same reason. Again, all omegas of degree 0 after shifting. So they can meet with everything. No signs are needed. No signs are necessary. Okay, then we get to the second term. This is the sum of all. So I can actually erase the sum here because I already used this sum to get this factor, right? I erasing the sum because instead of the sum I use this factor. Now the second term is sum over all p and q such that they sum up. Oh, okay, let it be r and s, which sum up to p, right? No signs are necessary. And there will be summation 1 over p factorial, 1 over q factorial. S factorial, r factorial, s factorial, f r of omega. You see, there will be not just one term of this form, but there will be exactly r factorial terms of this form, right? F, what next? S of omega. So after, so that's our first part. And the second part, which I almost forgot about, it is still important. It is plus 1 over p factorial, p minus 1 factorial, fp. And here, instead of delta omega, I can write something different. It is since you remember that omega verified the Mauer-Cartan equation, so delta omega plus 1/2 of omega comma omega is equal to 0. Right? So instead of this delta omega, I can write minus 1/2 omega comma omega. So it's minus 1/2 omega comma omega, and all the rest are composed of omegas. Nice. So now I can erase this finally and continue. So first term gives me fp minus 1, right? 1 over p minus 2 factorial, p minus fp minus 1, omega comma omega, and all the rest is also consists of omegas. All the rest also consists of omegas. Yeah, 1/2, because we also have 1/2 here. And that's 1/2 is really important because it will make this sum disappear when we add the last term, which is minus 1/2 sum over p, 1 over p minus 1 factorial, fp omega comma omega, and dot 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 omega in the end. These are the same, these two are give you the same sum. You see? So these two cancel out. Nice. Okay. So let me consider this term finally. You see, all this, so it's 1 over p factorial one over r factorial s factorial sum over all permutations. Sum over, okay, I think it's better to put it like this. Sum over p, 1 over p factorial, sum over r plus s equal to p. 1 over r factorial, s factorial, sum over all permutations sigma in s r plus s of this kind of terms. Fr omega omega Fs omega omega. I need to take care of this sum finally, right? As I told you, I can actually erase this term and just take all the shuffles of R and S components. And then I have just this. But all these terms will be the same. And there will be as many such terms as many different shuffles there are. But each shuffle is uniquely determined by the set of elements which you choose to be the first R elements. And remaining then will be the last S elements. So there will be precisely P choose R elements of this form. So let me continue. It is equal to sum over P, 1 over P factorial, sum over R plus S equal to P. This binomial coefficient P choose R, Fr omega omega, Fs omega omega. But this is equal precisely to P factorial divided by R factorial by S factorial. So this P factorial cancels out. And we just get the sum over all P and all partitions of E into the sum of two natural numbers, R and S, which of this kind of commutators. And now we can put 1 over R factorial here and 1 over S factorial to the right. And yeah, I think that's all, because as you can see, what we have on the right is precisely, oh yeah, one thing is missing, 1/2 is missing actually. I quite forgot that, yeah, here we need to assume that R is less or equal to S, I think. If you return to that formula in the end, I think I made a mistake when I wrote down the formula for the L infinity, because it is usually written in a different way, and I quite forgot all the details. So when you return to the to the formula of L infinity map, introduce 1/2 in front of this sum. It's either 1/2 of this, or you can should assume that P is less or equal to Q. Okay. In that case, what you have here is precisely 1/2 of the commutator of F omega. Yeah, this 1/2 is really important. I quite forgot about it. Okay? So we proved the formula that delta F omega is equal to, yeah, and also this minus, I think this minus was there. Sorry for this. It's hard to remember all the signs. Minus 1/2 of F omega. Okay, sorry for the signs. All the rest was done smoothly. Yeah. Okay. So it means that whenever we have two differential graded Lie algebras and an L infinity morphism between them, then we have a map from Mauer-Cartan elements on the left to Mauer-Cartan elements on the right. Of course, this map, this L infinity map, can be 0. So in order to ensure that we don't get something trivial, we need to fix something in this L infinity map. So let us return to our original problem. We have two differential graded Lie algebras, G equal to a space of polyvectors on M extended by H bar and shifted. This shift is different from the shift used in the definition of an infinity algebra. And H an infinity morphism. And H equal to the space of polydifferential operators on M extended by H bar and shifted. We need to look for an L infinity morphism, usually denoted by U in this case, from G to H. In order to avoid some trivial result, and also to make sure that the star product we obtain will be related to the original bivector, we might assume that the first term in this L infinity morphism will be equal to the Hochschild-Kosten-Rosenberg map. So suppose we can find such U. If we find U of this form, then we can define the star product on M by taking the element B, the Mauer-Cartan element B, equal to U of pi. That is to say, Bk will be equal to Let's put h bar here. Will be equal to h bar to the power k, 1 over k factorial, uk pi pi. As you see, the convergence is now provided by the fact that all formal power sums in the algebra H converge as long as the degrees of h bar grow indefinitely. Right? So if you put b equal to, so let me expand this equation. If b is equal to u of h bar p, you will have something like this. It will be equal to the sum over all p from 1 to infinity, h bar to the power p, 1 over p factorial, up of pi, comma pi. So what remains, and what was originally done by Kontsevich, is to define the remaining part, the missing terms in this infinity morphism. And that's actually the main result of Kontsevich formality theorem. You can now formulate it as volume. Let me begin with formulating this Kontsevich formality theorem, more or less close to the original form Kontsevich used to formulate it. Theorem. Let us take M equal to just the Euclidean space, affine space, RD. It's sufficient for us. Then there exists an L-infinity morphism U given by equal to the collection of maps UP, such that U1 will be equal to the Hochschild-Kostner-Rosenberg map. Observe that since this equation holds, this infinity morphism in fact induces an isomorphism in cohomology when you apply the degree 1 part of this infinity morphism, right? When something like this happens, infinity morphisms are called infinity quasi-isomorphisms as well. Just like usual quasi-isomorphisms are homomorphisms which induce isomorphism in cohomology. Infinity morphisms which induce isomorphism in cohomology, or better say, whose first term induce quasi-isomorphism in cohomology, are called infinity quasi-isomorphisms. So U can be sometimes called Kontsevich quasi-isomorphism. So let me describe briefly the construction Kontsevich used to get this quasi-isomorphism. To this end, I consider the following construction. We begin with considering the upper half space, upper half plane in complex plane. In complex numbers. So that's to say, H bar, so H is a set of all Z in C such that the imaginary part is greater than 0. H bar will denote the closure of H such that, so that's to say, the set of all Z in complex numbers such that the imaginary part is greater or equal to 0. We begin now with considering the sets, I forgot the word, actually, even in Russian. Okay, there is a special term which I totally forgot, even in Russian, but let me just use the description. First we consider the space Cn of all points Z1, Zn in H. And also C and M will consist of all points Z1, Zn in H, and M points P1 through Pm in the boundary of H bar. Oh, these are called configuration spaces. I forgot the word configuration. Okay. These configuration spaces are not compact. Our purpose is to define elements in Un of P1, Pn using some naive procedure, but with some non-naive coefficients. So let me first describe this procedure briefly. Every term here is a polyvector field. On D, on some Euclidean space, right? So in local coordinates, or in fact in global coordinates, pk will look like sum of some coefficients, functional coefficients, p alpha, pk alpha of x, d over d x I1, d over dx ik, I don't know, L, I don't know. Alpha is the set of this I1 through IL. Is a set of indices. And of course, here we can put wedges between these partial derivatives. As you see, this expression already has the form of polydifferential operator. There is some peculiarity of this polydifferential operator, namely, it has degree 1 in each variable, in each argument, right? And it is antisymmetric with respect to the change of arguments. But otherwise, it's just a natural polydifferential operator. What can you do with polydifferential operators to get other polydifferential operators? There is one thing you can do. You can substitute one polydifferential operator into another. You can also take wedge products, you can take cup products, you can take something else, but the most natural operation which produces new differential operators from some old differential operators is substitution. Right? How can you draw the procedure, the substitution that you can make up out of these n entries? You draw a graph like this. Every vertex of the graph will represent one of the polyvector fields. Every edge which exits it will either go to one of the polyvectors or it will go to the arguments, the ultimate arguments, because this should be a polydifferential operator, right? So you should be able to substitute certain number of functions into this polydifferential operator, right? So we distinguish those arrows which correspond to the arguments of the image by making them end on the straight line, on the boundary. All the other arrows will go from some vertex in the upper half plane to another vertex on the upper half plane. So something like this we'll have. By the way, I can substitute this polyvector into this polyvector as well, even though this polyvector is eventually substituted into this polyvector. It's also possible, right? Just by using some formal machination, some formal machinery. It's all very nice. The only problem is that you cannot just write down this formula and expect that the result will verify the Mauer-Cartan equation. It will verify the condition you put onto L-infinity morphism. So in order to avoid this, in order to escape this narrow place, Kontsevich introduces certain coefficients. So I'll denote this graph by gamma, and the corresponding polydifferential operator that you obtain by substituting these polyvectors into each other in accordance with the graph gamma by u gamma. Now we need some coefficients, some weights in front of these polydifferential operators to make sure that the construction, the ultimate construction, will verify the L-infinity condition. Kontsevich introduces these weights, these coefficients W gamma, by integrating certain differential forms against the space of all graphs like this. When I say that I integrated against the space of all graphs, I assume that the graph is uniquely determined by its set of vertices. All the arrows of this graph then can be drawn just by, either arbitrary, or you can draw them by straight lines. So the arrows are not important. Only vertices matter. So we need to integrate certain differential form against the space of graphs, but this space of graphs, this space, these configuration spaces, they are not compact. So we need to compactify them in order to be able to integrate something. So I am proceeding with compactifying these spaces. First, I observe that the function sorry, that the group G acts on C and M, where G is a group of affine transformations of the complex numbers of the complex plane. Here, A is real, positive, and B is just real. Right? Then, so I'll take C and M and quotient out the action of G. It means that I can actually assume that when I have a configuration of n points in the upper half plane and m points on the boundary, I can always assume that the m points I have are distributed between, say, 1 and 0 and 1. So the first point on the plane will be 0, and the last will be 1. I mean, we just renormalize the length of the distance between the first and the last point. And then we use B to shift it to the proper place. But the space is still non-compact. There are two types of non-compactness. One is very natural. It comes from the fact that I still can move the points here to infinity. It's not very hard to deal with. If it were just this, it wouldn't be much of a trouble. But there is another kind of non-compactness here. It is the fact that I should discard the sets where the I is equal to Zj for I non-equal to j. I told you that I take n points in the upper half plane, but these should be distinct points. So how do we deal with it? There are two different ways you can look onto this compactification procedure. One is formal. So let me begin with the formal construction. I consider the set of angles between various arrows, various points in my configuration space. Suppose we have Z1, Zi, and Zj. I consider the difference, and I take the argument of this difference. Right? I just want to make sure that I'm not this is not enough, unfortunately. I mean, I really would like to be able to restore all the configuration from just this data. Of course, if I just know all the angles, it is not enough. Even if I know the angles between Zi and Pk. P, let me recall that P are the P1 through Pn are points on the straight line. Okay? So I need to add just one more thing, it turns out. I need to consider the angle between Zi and Zj bar. Yeah. So now, if I know the position of the first point on the straight line is 0, and the position of the last point on the straight line is 1, or if there is just one point, you can just put it one point here, and that's enough, right? Then you can restore all the other points just by using these arguments. You can check it. It is just an easy geometry, elementary geometry. You can restore it by this. But what is an argument of a complex number? Argument of a complex number is an element in the group S1, group of unit vectors on the complex plane, right? So I obtain in this way a map from C and M into the direct product of certain number of circles. Namely, they will be precisely n times n minus 1 circles which come from this and these kind of angles, and also n times m angles of this type. So this is n. So I get this map, and this map is in fact an inclusion. There is a one-to-one correspondence. But the space on the right is compact. So now I compactify this by taking its closure, the closure of its image on the right. So C and M bar is equal to the closure of C and M inside S1 to the power n, inside this torus. This is the formal way to introduce this compactification. But you can do this a little bit informally, but there is I would prefer to speak about this in an informal way, but much more adequate in the sense that this informal way allows you to describe these spaces in a very natural way. So let me speak about the informal point of view on this compactification. So as I told you, the main problem is the situation when two points merge, come close to each other, right? Because when a point, some point goes to infinity, we can actually rescale this thing again, rescale it, and then this point will stay within a finite domain on the plane, but this will make other points merge to some fixed point on the plane. So we need to resolve these singularities. And this can be done in the following way. We look onto the points which come close together and use a kind of magnifying glass. Right? It will give us a normal, usual configuration of points. But this configuration will contain less points than the original one. So we can assume that we know what this compactification does for the points for this new set, right? And then we just add to the original configuration space this new set as a part of its boundary. Let us consider some examples.
How did we compactify this theorem? How did we compactify it?
I told you that I just considered this embedding of this C and M into the product of circles. And then you take the closure. If you take the closed subset, if you take a closed subset in a compact set, in a compact space, it is compact automatically. But it says really very little about the geometry and topology of this compactified space. To obtain some information, it's better to take a look onto this kind of informal but very convenient constructions. So let me begin with some examples. So we take C10, 0. That's a set of which contains only one point in the upper half plane and 0 points on the boundary. So there is no need to compactify it, because if you take the original quotient space, it's already compact. It will contain only one point. So there is no need to do anything here. It's more interesting to consider C1, 1. There is one point on the boundary which you can move into the origin, but then you'll still have the freedom to change the scale. So you can now rescale everything so that the distance from this point and this point in the upper half plane, I don't know what is the name of this point, P, will be equal to 1. So this space before compactification will be equal to the arc, the half circle arc. It is so even before the compactification. So when you take the closure, you'll get the half circle on just this, just the segment, because topologically, half circle and the segment are the same. Closed half circle on the segment. It's also interesting to take a look onto C01. There is no, that's again 1 point, because again you can just, you don't even need to compactify anything, because after the quotient out the action of the group, you can assume that this point is fixed, right? Nice. Okay. C02. Again, we have no points inside and 2 points on the boundary. But we can rescale them to be the points 0 and 1. The only problem is that we don't know the order of these points, so it can be quite the same, but with P and Q changing their roles. Right? So this will consist of 2 points. This and this. And finally, we'll have the most interesting part of the discussion of this set of examples is the configuration which involves 2 points in the upper half plane. C, 2, 0. So now we can assume that one of the points is okay. I think it is better to begin with a different thing. There are 3 possible singularities which we can run across in this case. The first singularity is that these 2 points, P1 and P2, will come together. Right? So but they will come together, but they will be far from the boundary. In that case, we can just choose one of them, announce it to be equal to the, I don't know, to the point square root of -1. Say P1 will go to square root of -1. You can renormalize it by using the group. But then using magnifying glass, we can forget about the boundary. The boundary is left behind, is beyond the scope of our magnifying glass. And now we can renormalize, rescale the distance between P1 and P2 and assume it is equal to 1. We wouldn't be able to do this if we had a boundary, because we're scaling for the second time will change the boundary, right? But this can be done, and this gives us the first component of the boundary of this set, of the set C0 to bar. A circle. There are two other situations when we need to intervene into the position of points. These two situations correspond to a case when these points are far away from each other, more or less, but one of them goes towards the boundary. Right? If we now forget about this point and magnify the position here, we can let this point get into the boundary. And thus, we'll get a configuration from C11 bar. So the boundary will correspond to the C bar 11. But C11, as I remember, was half circle. Was a half circle. The other half circle appears when we leave this point, P2, far away from the boundary and let P1 go into the boundary. So this will give us the upper half, the other half circle. And all what remains is to shade the area between these. So this gives us the I configuration, and that's the C20 bar. This point, by the way, and this point correspond to the case when both points P0 and P1 and P2 go into the boundary, and they both go into the boundary. But they can do this in different order. You can either make P2 go to the right of P1 and P1 go to the left, or you can change the order and let P2 go to the left and P1 go to the right. So this is the configuration C20 bar. In general, you can show that the boundary of CAB bar will consist of terms like following. You choose a set S of points here in A and let them merge together. And what you obtain there are two types of boundary like this. Will consist of C A minus S, to which you add the point, the remaining image of S points which you merge to one point. Okay? But it's not all, because you still can use magnifying glass on S and reproduce the configuration space of S points outside of the boundary. We forgot about the boundary. Or you can take two sets, S points in A and S prime points in B, and let S and S prime merge together. And that will give us the Cartesian product of CS S prime, precisely in the same way as before. Use magnifying glass on them, and this gives us this configuration space. And what remains is C A minus S, comma B minus S prime, to which you add one point. The image of S and S prime merge together. It is easy to see that the boundary of CAB will consist of such components. It means it gives us a way to describe the boundary, and it's crucial for our purposes, because what I'm going to do next is the following: is introduce the weights. As I explained, weights will be equal to the integration of certain differential forms associated with graphs. So let me first describe the graph. So let us have m points z1, zn in upper half plane, and m points p1, pm in the boundary. I'll consider graph gamma which verify the following conditions. So I consider graphs which verify the following conditions. First, it will be a oriented graph. That is to say, all edges of this graph will be decorated by arrows. Second, for every edge of this graph, its origin, its source, will be one of the points z bar through zn. Three. And no loops, no multiple edges, yeah. Multi-edges. Where I allow the edges to go in different directions between 2 points. This is possible. But I do not allow them to go in the same direction. Okay? Nice. Anything else? Okay. In order to introduce so let me choose such graph, and I order its edges. For instance, I fix an order of these edges. For instance, I can do this by ordering them in lexicographic order. I mean, the set of vertices of these edges is ordered, as I assumed, right? So I can say that, for instance, the vertex which which connects Z1 and Z2 precedes the vertex which connects Z1 and Z3, and so on. So this is the oriented graph with ordered set of vertices, an ordered set of edges. Then I do the following thing. I consider this set C2 bar, C2 0 bar, and fix a map phi from this set to S1. It can be done in different ways, but for me, well, I can fix just one particular form, so I just write down the formula. Phi of P and Q. P and Q are the points in C2 before you pass to the bar, right? Pass to the completion, to the closure. It will be equal to the argument of Q minus P divided by P Q minus P bar. As you see, it is a continuous function on continuous bounded function on this set C20 without bar, so it extends to a continuous function on this closure. Observe that phi of this inner S1 is just the angle. I don't know how to call this. The angle measure of the arc of this circle, which you measure from the vertical line in the positive direction. And also, if you consider the image of the upper interval, then it will go to just one point inside S1. Actually, any map of, with these two properties will suffice. Anything of this which verify these two properties is sufficient for our purposes. So I'm finally able to write down the weight. The weight which we attribute to the graph gamma will be equal to the following integral. First, we take the product for all points in the upper half plane of the normalizing factors 1 over star of this point factorial. So star of the point zk is the set of all arrows which exit this point. And mod star is just the number of these arrows. Then we have the following normalizing factor, 1 over 2 pi to the power n to n plus m minus 2. And finally, we have the integral against c bar and m. I put plus here and I explain this just a little later. But of the differential form given by the wedge product of d phi e for all edges E in the set of edges of gamma. So let me explain the remaining part of notation. What is phi E? We have a map from C bar and M into C bar to 0, given by forgetting all the edges except for the given one. So phi E is this map. We forget all the edges except the given one, except for the given one. Right? So you can now compose this map with the map phi, which I described here, to S1. And this will give you the a function on C and M with values in complex numbers. You can now differentiate, take the differential, the RAM differential of this function, and it will give you this one form. Now, what is C and M plus? That's easy, actually. As you remember, there are m points on the boundary of the upper half plane. As I explained when we talk about C02, there are two ways you can put these 2 points on the boundary. Either you can put the first one first and the second one second, or you can change their order. Here, in this case, there are exactly m factorial ways you can put these points on the boundary. That is, these different configurations, they are distinguished just by the relabeling the points on the boundary. Just to avoid this extra work, we remove this relabeling, which doesn't change anything, in fact, which don't change anything, in fact, and just demand that all the points on the boundary go in their natural order. The first one first, the second one second, and so on. And that's what we call, and this gives you a path component of the space C and M bar. So we just restrict our attention to this path component. That's it. Now the main result of Kontsevich is that what we have is sufficient to get the L infinity morphism. Few more finishing strokes are necessary to define this morphism in its full generality. So first of all, I fix the coordinates so if this piece of chalk is longer than 1 centimeter long, it will break down. It's inevitable. So we fix the coordinates x1, xd in Rd, on Rd. Suppose we have a graph gamma of the form which I prescribed. Gamma 1 through gamma n polyvectors. Homogeneous polyvectors of the same degrees, of some fixed degrees, and we also assume that the degree of gamma I is equal to the number of arrows exiting the ith vertex. Consider the map I from the set of edges of the graph into the set of natural numbers 1 through d. D is a dimension, as you see. So we put psi I from 1 to n equal to the pairing of the ith polyvector gamma I with dx I of the first arrow which exits this vertex. Wedge, 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 dx I of the last arrow which exits this vertex. This is just the coefficient of this polyvector corresponding to the coordinates I, E, 1I, E, 1, star Z, I, something like that. Very complicated, as you see. I also put, for all j from 1 to m, psi j equal to f j. I assume that we have exactly m functions on Rd which you want to plug into our differential operator. So let me go on with this notation. And we put, finally, for all vertices in gamma, psi of this vertex equal to the product for all edges which enter this vertex. Target of E is equal to V. D, I, E applied to psi I or psi j, depending on whether this vertex is of the first type or the second type. Right? Whether we have this or whether we have this. So it means that when we look into a graph, there are two types of vertices. Some vertices sit on the boundary, and some vertices sit in the open air, so to say, above the boundary. So above the boundary, we put this as the coefficient which corresponds to this vertex. And on the boundary, we put just the function. So we finally write down U gamma of gamma 1, gamma n applied to f1 through fm equal to the sum of over all maps I of this form, products for all v in v gamma this psi v, this expression psi v. And the last but not least is the ultimate formula. So this explanation was just the formalization of that informal point of view when you plug one polyvector field into another polyvector field to obtain the polydifferential operator. So finally, we just put un of gamma 1 through gamma n equal to the sum for all gammas with n m vertices, right? Right. Some for all. Okay, I think probably better to put m as a separate summation. So sum of all m's for all m's greater or equal to 0, sum of all gammas with n m vertices W gamma times U gamma of gamma 1, gamma n. So that's probably the most ingenious formula I've ever seen. You can prove that this construction actually gives you the L-infinity morphism we crave for. To this end, you need to differentiate Un and use Stokes' formula for W gamma. You remember that W gamma used to be integrals of some differential forms against manifolds with boundary, spaces with boundary. So by Stokes' formula, when you differentiate them, you can replace this by integrating over the boundary. Right? Then you use the construction which describes the boundary, which I explained, to prove that the construction will actually give you an infinity morphism. That's not an easy thing. And I believe that Kontsevich himself made pretty poor job explaining this in his original paper. I mean, he was very sketchy and omitted so many details that it's been, for a long time, it's been a kind of sport for various people to fill in gaps in his proof. But in this case, I think the idea is clear, and it's probably a good time for us to make a break.